What if every decision you've ever made spawned a universe where you made the opposite one? What if there's a version of you right now reading this from a different planet, in a different galaxy, having lived an entirely different life? That sounds like science fiction, but a growing number of physicists treat parallel universes not as a storytelling gimmick, but as a genuine mathematical consequence of how reality works. And the signs that they might actually exist are stranger than anything Hollywood ever dreamed up. Number 1. Quantum superposition. The universe splitting at every moment. The weirdest experiment in physics is also the most famous one. Fire a single electron at a barrier with two slits in it, and instead of going through one slit like any sensible particle should, it goes through both simultaneously and interferes with itself, creating a wave pattern on the other side. That only makes sense if the electron exists in multiple states at once, which physicists call superposition. Now scale that up. The many worlds interpretation, proposed by Hugh Everett in 1957 and now taken seriously by a significant chunk of theoretical physicists, says that when any quantum event happens, the universe doesn't pick one outcome. It branches. Every single quantum event, and there are astronomically many of them happening inside your body right now, spawns as a new universe containing that version of events. You measuring the electron didn't collapse its wave function. You split. The electron split. The whole universe split. And the scary implication is that this branching never stops. Right now, trillions of copies of you are diverging from this moment because of quantum events happening at the subatomic level in your own neurons. The math behind Everett's interpretation isn't fringe speculation either. It's the same wave equation that correctly predicts quantum behavior in labs around the world. Number 2. The cold spot, a bruise left by another universe. In 2004, astronomers mapping the cosmic microwave background, which is the faint afterglow radiation left over from the Big Bang, found something that didn't belong. A massive region of sky roughly 1.8 billion light-years across was significantly colder than everything around it, almost a perfect void where matter and energy seemed to just vanish. Scientists named it the CMB cold spot, and for 20 years nobody has satisfactorily explained it. The leading conventional explanation is a supervoid, a genuine cosmic region with less matter than average. But when astronomers measured the supervoid that overlaps with the cold spot in 2015, it wasn't nearly empty enough to account for the temperature drop. Rangaram Cherry of Caltech published a paper in 2015 pointing out that this and other CMB anomalies could be explained by our universe having physically collided with a neighboring bubble universe at some point after the Big Bang, leaving a bruise in the sky. The collision imprint, according to this model, would look almost exactly like what we see: a cold, anomalously smooth region where two different universes once grazed each other. We are potentially looking at a scar left by another universe, and it's just sitting there above our heads, enormous and silent, daring us to explain it some other way. Number 3. Inflation theory, the machine that manufactures universes. Almost every cosmologist accepts that the universe went through a period of inflation immediately after the Big Bang, expanding from something smaller than a proton to something the size of a grapefruit in an almost incomprehensibly brief fraction of a second. Alan Guth developed this model in 1980 to explain several otherwise baffling features of the cosmos, like why the universe looks so uniform in every direction and why its geometry is so perfectly flat. The thing is, when you work through the mathematics of how inflation started and stopped, you hit a serious problem. There's no clean mechanism that stops inflation everywhere at once. Instead, the math suggests that once inflation starts, it keeps going in some regions of space even after it stops in others. The regions where it stops become bubble universes like ours, with their own physical constants and structures. The regions where it continues keep inflating and spawning more bubbles. This model, called eternal inflation, was an unexpected consequence of inflation theory, not a feature physicists bolted on to be creative. It fell out of the equations, whether they wanted it or not. Paul Steinhardt, one of the original architects of inflation theory, has called this an embarrassment because the theory that explains our universe also predicts an infinite number of others, and we can't get rid of that prediction without breaking the parts of the theory that work beautifully. The multiverse wasn't invented. It was discovered hiding inside the math. Number 4, the fine-tuning problem. Why our universe seems rigged. The physical constants of our universe are suspiciously perfect for producing complexity. The strength of gravity, the mass of electrons, the cosmological constant governing the energy of empty space, All of these values fall within extraordinarily narrow ranges that allow atoms, stars, planets, and eventually life to exist. Change the cosmological constant by 1 part in 10 to the power of 120, and the universe either collapses immediately or flies apart so fast that matter never clumps together. Change the strong nuclear force by just a few percent, and stars can't produce carbon. Physicist Fred Hoyle called this the appearance of a put-up job, and that discomfort has never really gone away. There are basically two uncomfortable explanations. Either our universe was deliberately designed with these values, which is a theological claim, not a scientific one, or there are an enormous number of universes each with randomly different constants, and we necessarily find ourselves in one where the values permit our existence. This second explanation is called the anthropic argument, and it requires a multiverse to function. Without many universes to draw from, the fine-tuning looks like a miracle that demands a miracle worker. With an infinite multiverse, it becomes pure selection bias. We couldn't possibly be asking the question from a universe that didn't permit us to exist. Number 5. Déjà vu, your brain glitching or something stranger. Most neuroscientists explain déjà vu as a memory processing error, a brief misfiring where new sensory input gets tagged as an old memory before your brain catches the mistake. That's almost certainly the correct explanation for most cases. But some researchers have pointed out that the phenomenon is strange enough in its mechanics to at least invite curiosity. The feeling isn't just familiarity. It's a precise and overwhelming certainty that you have lived through this exact moment before, often paired with a creepy ability to predict what happens next a fraction of a second before it does. In a multiverse framework where parallel timelines can theoretically overlap or share structural similarities, déjà vu gets an unusual re-examination. Physicist David Deutsch, one of the strongest advocates for the many worlds interpretation, has argued that quantum coherence effects could in principle allow subtle informational bleed between branches, though he's careful not to overstate this. The mainstream view remains neurological, and fairly confidently so. But déjà vu sits in a genuinely unresolved space because we still don't fully understand how consciousness integrates moment-to-moment experience, and until we do, the possibility that we're occasionally detecting echoes of adjacent branches can't be completely closed off by science, only noted as deeply unlikely. Number 6. The mathematical universe hypothesis. Reality is just equations. Physicist Max Tegmark at MIT argues for something called the mathematical universe hypothesis, which pushes the multiverse concept to its most extreme possible conclusion. The idea is that our universe doesn't just follow mathematical laws, it is a mathematical structure. Physical existence and mathematical existence are the same thing. Any self-consistent mathematical structure exists as a physical reality somewhere, and there are infinitely many self-consistent mathematical structures, meaning there are infinitely many physical realities. This sounds like pure philosophy, but Tegmark grounds it in a straightforward observation. Physicists have never found any aspect of reality that can't be described mathematically, which is an odd coincidence if math is just a human invention we happen to apply to a non-mathematical world. If the hypothesis is correct, parallel universes aren't just possible, they're mandatory and infinite in variety. Some would contain the same physical laws as ours, but different histories. Others would have entirely different constants. And others would be so structurally alien that the concepts of space, time, matter, and energy wouldn't apply at all. The unsettling part is that Tegmark's hypothesis is internally consistent and makes predictions that are at least testable in principle. It hasn't been falsified. It just hasn't been confirmed either, which means we genuinely cannot rule out that every mathematically coherent reality exists somewhere and that our universe is one entry in an infinite catalog. Number 7. The simulation argument, nested realities as a multiverse mechanism. Nick Bostrom's simulation argument, formalized in 2003, proposes that at least one of three things must be true. Civilizations almost always go extinct before developing the ability to simulate conscious realities. Advanced civilizations almost never bother to run such simulations, or we are almost certainly living in one right now. The statistical logic is uncomfortable. If even one civilization in history develops the computational power to run realistic simulations with conscious inhabitants, and chooses to run many of them, the number of simulated minds would vastly outnumber the biological ones, making it statistically probable that you are simulated. And if simulations can contain other simulations, which is a reasonable assumption, the result is an infinite nested stack of realities, each one a parallel universe of sorts from the perspective of its inhabitants. Physicists like Silas Bean at the University of New Hampshire have even proposed that a simulated universe might show artifacts in the structure of space at very small scales, like pixels in an image. And interestingly, some quantum gravity theories do predict a fundamental granularity of space-time called the Planck length. Nobody is claiming that's proof. But the overlap between what a simulation would predict and what we actually observe is close enough that serious researchers have spent serious time on it. Number 8. The signs point somewhere, but not clearly enough to see. Taken individually, none of these signs constitute proof. The CMB cold spot might eventually get a better conventional explanation. Quantum many worlds remains one interpretation among several. Eternal inflation's untestable bubbles frustrate experimentalists, and fine-tuning arguments are technically compatible with a single precisely configured universe. But taken together, what's striking is that parallel universes aren't being invoked by people who want them to exist. They keep falling out of independent lines of physics by accident, each developed for entirely different reasons, and arriving at the same inconvenient destination. The universe keeps handing physicists math that points beyond itself, and physicists keep trying to find a way to make it stop, and mostly failing. Whether parallel universes exist or not, the fact that our best theories keep predicting them says something deep about the limits of what we can know from inside a single universe. We might be asking questions that our reality structurally cannot answer, and that might be the most unsettling sign of all. Thank you for watching and sticking until the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next.